Okay, we're going to talk about how we can write complex numbers in polar form. Okay, so this is just building on things that we've already done, thinking about the polar form of numbers. So remember, for polar form, we need r, right? The distance or the length, or the distance from that point to the origin, and our theta, right? And we've already been talking about the magnitude of a complex number being this distance here. And so now we just need to think about this theta. So just like with polar numbers, or the polar form of any number, we have our x value here and our y value here. In the case of complex numbers, this is our real part and this is our imaginary part, right? So if this is our theta, we can write that x is going to be r times cosine of theta, and y is going to be r times sine of theta. And r is going to be the square root. We've already talked about this using the distance formula of x squared plus y squared. If this is our complex number, z equals x plus yi, then we have z equals r cosine theta, replacing x with that, times I times r sine of theta, right? This is our x value and this is our y value. And we could factor the r out to get r times cosine of theta plus I sine of theta, okay? This is, so we've been talking, so r is the modulus of our complex number, or we've been talking about is the absolute value, right? That distance. We call that the modulus. And theta we call the argument. So just like with polar form, r is this distance, and theta is this angle here. So our complex number is r times cosine of theta plus I sine of theta. This is the polar form of a complex number, okay? And we sometimes, if you notice, this is a C, this is an I, and this is an S, since this is kind of a long thing to write, sometimes we write this as R CIS cis theta. This has nothing to do with like gender identity or anything. This is just short for cosine plus I sine theta. Okay, these are the exact same things. This is just like a shortcut. Okay, and we can always think about this drawing if we ever get confused or forget what this looks like. It's not hard to drive this, right? We could draw this. We could say this is x, this is y, this is x plus yi, this is r. This is, our x value is going to be r cosine theta, our y value will be r sine of theta, and we could substitute those in. Okay, so this is the polar form of a complex number. So let's do some examples. Suppose we have a complex number, it's an easy one, 4i, and we want to write that using polar coordinates. Okay, so we want to have it in the other form. All right, so first we find the modulus, or it would really be the absolute value of this complex number. So in this case, our x value is 0. Whoops. Our x value is 0, and our y value is 4. Right? So we just plug those in, find the square root. And our modulus for this number is 4, which kind of makes sense if you imagine in your head. We'll look at it in just a minute, but what the graph looks like. This number is 4 units from the origin. Okay, so our modulus is 4. And we know that, so x is going to be r cosine of theta. We know that x is 0. So what does theta have to be? This is like this is like a trig equation, right? What does theta have to be if cosine of theta is going to be 0 to make this equal 0? Well, pi halves, right? Cosine of theta has to be pi halves if we want cosine of theta to be 0. Okay, so we know that theta is pi halves, and we can write this as 4 times cosine of pi halves plus I times sine of pi halves. Or we could write that as 4 times cis pi halves. Okay, and obviously if we were going to graph this, so just just graphing this number here, 4i, we're going 0 in the real direction, 4 units in the imaginary direction, or the y direction. So there's our point. Our modulus, or absolute value, is 4, and our theta is going to be pi halves. Okay, let's do another one. It's a little bit, this has an x and a y value, a real and an imaginary part. So first let's find our modulus. Same equation. So minus 4 squared plus 4 squared, square root of 32. We get that our modulus is 4 times the square root of 2. Now, how are we going to find our theta? Well, we know that cosine of theta equals x over r. So just like we'd used when we're finding polar coordinates, okay, cosine of theta is x over r. We know our x value is -4. Our r value is 4 times the square root of 2. So cosine of theta equals -1 over square root of 2. That's the same as square root of 2 over 2. Back to the tables, our trig tables. We never get away from those things, right? You still need to know those values. Cosine of what angle equals negative square root of 2 over 2? The answer is 3 pi fourths. Okay, and the way we know that is from our trig table. Okay, so there's our theta. We have our r. So it's going to be 4 times square root of 2 times cis of 3 pi fourths, which would be the same as cosine of 3 pi fourths plus I sine of 3 pi fourths. But you could write it like this. Okay. What if we want to go the other way? What if we have a polar form of an equation and we want to write it in rectangular form? Well, we can just evaluate these things. If they're values from our trig tables, we know them because we know our trig tables. Or if it's some weird angle that we don't know, we can just use our calculators. Right? So let's see. Cosine of pi sixths, I'm sure you all remember, is square root of 3 over 2. Sine of pi sixth is 1/2. So we just plug those in. 12 times square root of 3 over 2 plus 1/2 I. Now we just do algebra. Okay, we multiply 12 times these, 12 times this, and 12 times that. And simplify, we get 6 times square root of 3 plus 6i. So this direction's a little bit easier, right? Going from rectangular to polar, we have to find the angle, which I think is a little bit tricky, using the inverse trig table. Evaluating these trig functions is a little bit more straightforward, I think.